About 2.5 years ago, I was in a room with about 5 or 6 other engineers at Skyscanner, and we were tasked with something I thought should be a pretty simple thing to do. We basically had to figure out where does our company's revenue come from, right? We thought, or at least I thought, we should have a pretty good grip on that already. What I mean by that is we actually had to understand how the events that drove our revenue flowed through our data platform and ended up in financial reports. And the reason we needed to do this was that we now had to comply with US regulations known as SOX, or Sarbanes-Oxley. And these regulations basically mean that you need to be able to show that no one outside or inside of your company can change the events that would eventually show up in financial reports in any way that could change the numbers or misrepresent the data. Now, luckily, we knew that our revenue events were basically all from a single source. There was only one type of event that really drove revenue, and this was referrals, when users clicked on a specific recommendation that we gave them. So it should have been simple, right? We had this one event that we had to understand the full flow, but it wasn't. It took us weeks to actually get the answer and have enough confidence in our answer to make a recommendation on how can we secure this pipeline. And that really made me pause and ask, how did we get to this place where no single team or not even a single person understood our pipeline well enough, or understood even this one event well enough to understand the full picture and the full flow of how it ends up in financial reports. So in this talk, I want to explore that a little bit and tell you a bit about the history of the data platform at Skyscanner and how we got to this point, what we've done since to try and course correct. And hopefully through the lessons that I'm going to share with you, you can avoid some of the traps that we fell into when we were building a streaming pipeline. And I hope if you are in the position that I was in a few years ago, that you would manage to avoid these mistakes, and you and your consumers of data would be better off for it. So very briefly about myself, my name is Herman. I work at Skyscanner. If you haven't heard of us, we basically make it very easy to find affordable flights. Our mission is to lead the global transformation to modern and sustainable travel. So we do that currently by providing you with very affordable flight options, but you can also sort by price and comfort or carbon footprint even, and we recommend you the best flights and from city to city, along with some other things. We're very well known in Europe and in Asia. We serve at peak about 100 million travelers every month. So if you haven't heard of us, I recommend you go check it out. It's a very, very useful product. Now, our data story started very much like I think most companies, or many of you here would find this familiar. We had data stored in all sorts of different places. We had Mixpanel, we had Google Analytics, we had something we lovingly referred to as the Cube, which was a big OLAP database hosted on internal servers. And we very quickly ran into issues with this system. The primary one is, of course, when you're looking for a single answer, you want when you have a question, you want to get a single answer, not 3 different answers to the same question, which happens when you have different sources of data. And so we wanted to consolidate that. And we also found that the scale that we were now operating at and the amount of data we were getting was just impractical to do this batch loading on a daily basis and load everything into this OLAP database. So we wanted something that was more real-time, and along with the move to the cloud about 4 years ago, we moved to AWS, and we decided to also look into streaming pipelines at the same time. And that's, in a nutshell, how we went from batch to streaming. And this is essentially what our very first architecture looked like. Interestingly, we weren't really sure whether this streaming thing was going to stick. So we put Kafka in the middle there, and we made an interesting decision early on to just say that 3 different types of data will all go through the same Kafka cluster. We'd have metrics that go to OpenTSDB, which is a time series database. It's open source, highly scalable based on HBase. And our users would be able to query that through Grafana. And there would be business events, which is going to be my main focus today, which we sent on to S3, and then that would be queryable through Athena or Redshift or Spark or what have you. And that's more for long-term storage. And then there was also application logs, which we also sent through the same Kafka cluster, but to Elasticsearch and queryable through Kibana. So our users could get real-time insights into how their applications are performing and what errors are being logged and so on. And those were three very different kinds of things with three different syncs, essentially. But they all flowed through the same Kafka cluster. And we also instituted a convention early on that we'll use protobuf for everything. So everything in the Kafka cluster was protobuf. Our servers were able to directly connect to Kafka and send protobuf there. We had an HTTP API in front that spoke REST, so mobile clients and desktop clients could talk to this API and then forward the events as protobuf to Kafka. And things were great. We didn't know whether this was going to catch on, but it did. Like very soon, we were serving about 100,000 events per second through this pipeline, and pretty soon people started asking more of us, of course. So they asked, hey, this is cool, we have all this data in Kafka now, but actually we'd like to do some transformations on it, we'd like to add some information to our topics and so on. So we did the typical stream processing thing. We added Samza, which is a stream processing software, open source software. You can think of Apache Storm as a similar thing if you don't know Samza. We found it was a bit difficult to get set up with that. It was a bit too much to know to actually get started with Samza, so we made a templated version of it where basically data platform users could do a couple of clicks and change one or two lines of code, and then they have a stream processing system up and running, and they can read topics and write back topics to Kafka. And this was great. This satisfied everyone. They were starting using it. They were using it to merge topics together, to split topics, to add more information to topics, to add information from third-party APIs, all sorts of things were going through Kafka and through Samza, and it was doing all these things. And at the time, there was this talk about this concept of the single unified log. We didn't really feel like this violated it because we still had this single source of truth, right? If all the data was still going through Kafka, it's still a better situation than we were in before, where we had all these different sources of data. You can still kind of pull the thread through the whole pipeline with Samza just being a part of that. So it was fine. Life was grand. A platform was being used. We were happy. It was providing insights. It was driving reports. But it was in that room 2.5 years ago when we were filling up whiteboards, trying to figure out where our revenue came from, going through lots of GitHub code, where I realized maybe we had become the victims of our own success. Because when we started looking into it, we saw that really like our events were going through an epic journey. So it started out from the mobile device, and then it would go to the server, serving the referral in this case. That server would send our event to Kafka as protobuf, and then the very first Samza job would pick that up and maybe add some more information to it. In this case, we wanted some device information added to the topic. Okay, that's great. Then another Samza job appeared and picked up that second topic, added some more information to it. This time, maybe we wanted an estimate of the revenue that we're going to get from this event, something like that. That we weren't able to get initially in the first API call. And then another job, and another one, and another one. I don't know, maybe this seems familiar to you, but there was a long line of Samza jobs, essentially, all leading through, and then eventually our revenue event ended up in S3. But no one really had the full picture of this, and like near the end of the pipeline, we had a deduplication Samza job, because after all these network hops, we've probably introduced some duplicates now. We'd like to remove those, and then before we send them to S3 for long-term storage. And the problem was there was no automated way that we had, initially at least, to know how these topics were related to one another or like what the lineage was. So my first lesson here is that Conways Law is true for data platforms. If you haven't heard of Conways Law, it basically says an organization which designs systems are constrained to produce designs which are copies of their communication structures. And I substituted systems here for data platforms because when you look at our revenue pipeline, you basically see a mirror of Skyscanner's organizational structure. Like, there was the first team producing the event and kind of firing and forgetting about it, because it was their job to send the event, and it wasn't their job to actually make sure it made it all the way to the end, to the archive. The next team would pick up that topic, they would add some more information that they needed, and then the next team and the next team, through basically several organizational hops all the way through to the archive. So that's why no one really had the whole picture. Like, it was all going through all these different teams, and we had essentially created a rather complicated system inadvertently. And there was a reason for this, though. Like, when we created our data platform initially, we wanted it to be self-serve. We said, you know what, we're a small platform team. We're like 10 people in a company of about 1,000. We can't possibly know every data set that's going to be going through our platform. We would simply become a bottleneck. So we like to call ourselves data agnostic. That's one word for it, or having a self-serve platform is another word for it. But what we maybe didn't realize at the time is that metadata then becomes absolutely critical. Or maybe we did realize it, but we didn't realize it quite enough. Because when you have a self-serve architecture, your users and you need a lot of metadata to actually make sense of what's going on in the system. So let's talk about metadata just a little bit. Because we did have metadata, right? But if you were eagle-eyed in that architecture diagram I showed earlier, maybe you noticed something missing. And that was a schema registry. We actually didn't have a schema registry. Even though we used protobuf, or if you use Avro, it would be similar. Like, usually people would use something like Confluence schema registry to keep track of which topic uses which schema. So how did we actually do that? How did consumers know which schema was being used in a topic? Well, it was convention. Very early on, we realized, yeah, this is going to be a problem. We need to know which topic is using which schema. So we came up with this really simple convention. Actually, one engineer came up with this clever convention, which is basically a dot-separated string for every topic. So every topic at Skyscanner looks like this in the Kafka cluster. It's like environment.servicename, .eventname, .schema, .message. And environment is something like production or sandbox, and then the name of the service, and so on. So pretty soon we had topics like prod, identity service, audit log, identity audit message, which is pretty good. Like, I know it's using the audit message protobuf schema. I know which service is producing this. And essentially through this convention, we knew what was in every topic and how to read it without having any kind of schema registry, which was really neat. That was nice. Like, it saved us a bunch of time. We didn't have to go implement a new API. We were a small team. We didn't have time for that anyway. So this convention got us really far without doing a lot of work, without setting up a schema registry or anything like that. Of course, pretty soon we also had topics like prod flying circus.applog message, raccoon bandit experiment with bandit at metric. They tell you a little bit less, I guess. It comes down to how useful of a name the teams choose for their services in a lot of cases, but at least we know more than we would have known without this kind of convention. So I'd like to distinguish between three types of metadata. Now, I'd say there are maybe these three: descriptive, structural, and administrative types of metadata. So with descriptive kind of metadata, we're talking about the question, or we're trying to answer the questions that are basically, what does it mean? Who owns it? What does it contain? Where does it come from? That kind of question you're trying to answer with descriptive metadata. Structural metadata is, how does it relate to other data sets? How is it organized? How is it sorted or partitioned? And administrative metadata is more about how far does it go back? How frequently is it updated? How large is it? How complete is it? Like, these are all really important questions. And what we found was that we kind of covered the first one. We had some descriptive metadata by virtue of using the topic naming convention. We had a little bit of structural metadata because we used protobuf. If you're not using a structured schema like protobuf or Avro, I highly recommend you go out and do that and get yourself a raise. But we kind of had that, but we didn't know how datasets related to each other. So we had that key component of structural metadata that was just completely missing. At administrative metadata, if we had it, we weren't exposing it to our users. So you may as well say we didn't have it. But we did know if we really wanted to find out, we could find out answers to some of these questions. So the second lesson here is that metadata is absolutely critical. We started asking our users to manually enter the lineage before saving events to S3. And ideally, we would have done this from the start, of course. Ideally, this would have been completely automated as well, but it wasn't. And we were now trying to course correct. And it's better to start late than not ever. Tools like the schema registry would have been a start, but it's not the full solution. The schema registry itself also only tells you about the kind of schema that's in there. It doesn't give you all three types of metadata. You kind of have to think about how you're going to provide that to yourself and to your data platform users. So I'd like to compare this to this XKCD comic, which many of you may have seen already, of characters going through Jurassic Park, right? So I'll quickly explain, when characters are in the same scene, the lines are close together. When they're not in the same scene, or if they're far apart for some reason, the lines are further apart. And time is on the x-axis, so as time goes on, you can see the raptors, for example, start out together and then they split apart. They don't make it all the way through, as some of the characters also not make it quite all the way through, as you might expect in Jurassic Park. But yeah, it's a nice view of basically what's happening in Jurassic Park. And in this analogy, I'm basically saying topics in Kafka are a bit like this. They can start out together and then get split up, or they can get merged halfway through, or some of them make it all the way through to the archive, some of them don't. And we thought our pipeline looked like Jurassic Park, but really it looked more like Primer. Everything starts out completely fine, with 3 characters, and then as time goes on, you start time traveling, and it just loses all semblance of traceability, and your audience are left scratching their heads. So the situation would have been better with metadata, but that's not the full answer either, because our users still evolved a really complex system while we were kind of looking away. And by having very few restrictions on what you can do and what kind of transformations you're allowed to do, we kind of harmed the usefulness of our platform in the long run. So our system was very simple, but the data was not. And that brings me to the third lesson, which is that data engineers control the plotline. So what do I mean by this? Now, we've all heard of spaghetti code. It's basically when you have code that's very hard to trace. It's crossing across different files and different methods, and you can't really follow what's going on. Now, spaghetti code is very easy to recognize. But in a data platform, you don't actually see it in your code base. You could have a data platform that has very, very modular code, a shining example of clean, modern coding designs, but meanwhile, your users are the ones producing the spaghetti, and their data is actually where the spaghetti is. It's not always easy to see. But the controls that you put in place on your users, and you really have to think about this very carefully early on, what controls are you going to put in place to make sure that you end up with a plotline that looks more like 12 Angry Men rather than Primer. Now, I enjoyed both these movies. I recommend you go out and watch them if you haven't. But I would rather have a plotline like 12 Angry Men for my data platform than for one like Primer. Right, so we kind of knew what the problems were. We knew that SAMSA, or processing jobs in general, were causing us issues because they were on the path to our data lake, to long-term storage. And this complexity wasn't even the only problem. We had other things too. We knew that if one of these SAMSA jobs failed for whatever reason, then the topics that they output would also impact downstream SAMSA jobs. And users would come to us and say, hey, this topic disappeared, where did it go? Where do I find the owners? And we would kind of say I don't know, it's, we're data agnostic, we don't know. So that was not a great situation to be in. But also, moreover, when any of these SAMSA jobs had a bug, which would inevitably happen from time to time, they'd be producing data that would be incorrect, and someone would discover it after some time. Like yesterday, we saw a talk by Great Expectations, which could definitely like help with this kind of problem. But the fact remains, like when we discovered a bug like this, we would then have to replay data through the pipeline somehow, without affecting all the other SAMSA jobs that might be depending on these topics. And we don't really understand what might be the implications. We don't understand what this could mean for duplicates necessarily, especially when you're talking about replaying weeks of data. You could have all sorts of unpredictable problems. So this was affecting our ability to really analyze the data and to issue reports reliably. And we decided, we're just going to do away with that whole link. We're going to say, let's go straight from our HTTP API to S3. You may have noticed that the servers are now also communicating with the HTTP API. Like that was something we did somewhere in the middle, because we realized that when a lot of servers spin up a lot of containers, they all open connections to Kafka, and you run out of file handles, and that caused problems for us. So now everything was going through an HTTP API, and we were enforcing protobuf essentially, which is good. But now we kind of want to go straight from that API to S3. And you can't just do that, because if you were to simply write every request to S3 directly, you'd get very, very tiny files. You kind of need some sort of queue in the middle, as you all probably know. So this is kind of what we did. We decided, okay, we'll split our HTTP API. We'll make it go into two routes. We'll go, one way is the Kafka route, where we go with metrics and logs and events. And the other route would be Kinesis. And that would be consumed by Flink, and Flink would be writing it to S3 every 15 minutes. Now, we chose Kinesis not because it's necessarily a better choice than Kafka. It was easier for us to roll this out in multiple regions. It's managed for us. And Flink is a good abstraction layer. It's stateful. It allows us to do this writing to S3 in a kind of an easy way, without a lot of overhead. And what you might notice here is that there are no transformations on this. This is a lot more like 12 Angry Men. It's just a straight line. And this is kind of how we went from streaming to both batch and streaming. Like, you may say these are mini batches because we're writing them every 15 minutes. But the point is, there are no transformations, and we're all kind of going to the archive directly. Of course, though, people still needed transformations. So we said, that's fine. You can do transformations. You just have to do them on the archive. And we specifically said you can use Spark for this. But we learned our lesson. We said, if you're going to do a transformation, you need to register that somewhere. And we have this data catalog where we register transformations so we can understand the flow of data this time. We also favor configuration over code whenever we can for transformations, so that it's easier to track this kind of thing. And we even added some nicer things to this catalog, like measuring the completeness of the data, so we can have some more metadata in this way. And we were hoping to even verify ownership. Like in our topic naming convention, we kind of relied on honesty, like services really using their real name or a name we could find somewhere in the catalog. Now we have the opportunity to really verify this with like JWT tokens or something along those lines. So this also solves the replay problem to some extent, because transformations on the archive are repeatable. And this is something kind of fundamental with streaming pipelines that we don't often talk about, I think. When you do your transformations on S3 and you had a bug in your Spark job, for example, you could fix that bug and run it again on the same time frame, and the data would be replaced in place, and you don't have to worry about how it's going to affect other jobs necessarily, because you know which jobs need to be retriggered. You retrigger them again. You don't have to worry about duplicates being introduced or anything like that. So it was a bit simpler to manage the correctness of our reports, at least in this way. So the lesson here is that repeatability is important. Now, yeah, like I said, streaming pipelines kind of have to choose between doing replays, which could be complicated, and accepting errors as permanent. Now, I'm not saying it's impossible to do replays. You definitely can. You just have to think very carefully about how you're going to do them without introducing duplicates. I think if you have a clever partitioning scheme from the very start and you know how you're going to do replays in a way that's safe and predictable, then it's totally fine. But we chose to go a different route and kind of just avoid that problem altogether. So you really need to think quite hard about how replays will work. And in batch processing, transformations can run anytime, and you can do them again anytime. And it's just simply a bit easier to manage. So going straight to the archive kind of gave us a mix of both worlds, because to be clear, we were still sending our business events to Kafka as well. So you could still get those real-time metrics. You can still derive metrics. You could still run your SAMSA jobs. That was also fine. So you can get those transformations, but we just said, please don't send those to the archive. When we do reports, we want the data to be correct and reliable, and we need to be able to fix it in the future if something was wrong. So we kind of get the benefits of both, but also the downsides of both. One downside is now we have to maintain two code bases to do transformations. And it's a problem we haven't really solved yet, to be honest. We do Spark transformations, and we still have SAMSA transformations. Two code bases are a pain. We're thinking Spark streaming might help here. But honestly, it hasn't been a big problem. Like, most of our use cases for transformations were actually meant for the archive, and you kind of just need it there most of the time. So to quickly recap everything, the takeaways are that Conways Law is true for data platforms. Metadata is very critical. Data engineers control the plotline, and repeatability is important. Now, the lucky thing for me is that because Conway's Law is true, how these rules apply in your specific case will be different. It will be based on what your organization looks like and what your structure looks like. In our case, we decided to split and create this kind of dual batch and real-time architecture known as Lambda architecture. That worked for us. It might not work in your case, but it's something you need to consider. And I will say, though, that I think no matter what the size or makeup of your organization, having a self-serve data platform makes a lot of sense. As your organization grows, you'll become a bottleneck if you don't allow your users to use data themselves, make transformations themselves, do their own thing without you being the middleman as a data engineer. And then, as a data engineer, you need to be conscious of the controls that you put in place. And this isn't necessarily only a lesson for data engineers. It's anyone building pipelines, anyone doing transformations. You need to be aware. Like, having too few controls in place could really impact the quality of your data in the end, could really impact the interpretability of the data in the end. But having too many controls could harm adoption, on the other hand. So my recommendation here would be to aim somewhere in the middle and kind of tighten the screws as time goes on. Get people using your platform with some restrictions, and then if you see things like they're losing the plot, so to speak, you can kind of add some more restrictions as necessary. And so, yeah, then repeatability is important, but often overlooked. And if, like in our case, your streaming pipeline is also on the path to your data lake, you should really consider what happens when things go wrong. Like that is something really important to think about very early on. And we decided to go with this batch architecture because that simply avoids the problem. Maybe that's a good option for you as well, maybe not. But yeah, if you take these lessons to heart and if you do things right, then I hope, with some luck, you won't ever find yourself in a situation like me where you're trying to figure out where your company's revenue comes from. And that's me. Thanks.
Thanks for the talk. What does your data catalog look like?
It's a pretty simple database right now where we just capture some information. Like, yeah, it's basically a REST API where we capture this. It's kind of internal, still pretty new, to be honest. But yeah, what would you like to know about the data catalog specifically? Like,
yeah, I don't know. I was just wondering if you use a service or
Yeah, I think there's a lot you could do in this space. We're kind of still feeling out how to do that exactly. We we have like a REST API where we register at least the very basic transformations, especially merges of topics. We're interested in capturing that. We have a rule actually, like in my diagram it looked like 12 angry men. In reality, we actually have something that's a bit more like an n-to-one mapping. Like you're allowed to merge topics from many to one before they go to the archive, or before we commit them permanently to the archive, and that's configurable through this REST API. So that's kind of what it looks like. But yeah, still a lot of work to be done in that area. We also have something like I mentioned about completeness. That API is able to actually tell you over a long time span how complete was the data based on like GUID, for example. We measure like how many of the events were received on the one end, how many were received in the archive, and then we can tell you, okay, so this data set is 99.9% complete. You can probably kick off your reports or kick off your transformations. Yeah, that's also a REST API that we provide.
I have seen that every events are coming into the HTTP API, yeah?
Mm-hmm.
And it's quite a tricky just to create API that suits mobile platform, desktop platform, and all the rest. Do you use some kind of open source solution, or you developed it by yourself and maintained by yourself? How it's going?
That's a good question. We did actually develop this on our own. There are open source solutions out there now, I believe. I think Confluent offers one. I'm not sure, but we did develop our own solution written in Go in this case. And it's not that hard, I would say, to do because it's stateless. And it's basically only taking JSON and converting it to protobuf, which is not a very expensive operation necessarily. We did have to optimize it quite a bit for the kind of scale that we're dealing with, but it scales horizontally. Because it's not stateful, it's not that hard. It's maybe not as hard as it seems. But it did buy us a lot in terms of like redundancy across regions, in terms of consistency of our data, because now we can put some basic checks in place to validate the quality before it goes into Kafka. Things like that. It is definitely worth doing, even if it is a lot of work.
Why Flink versus using Firehose to write to S3?
Oh, good question. Firehose is essentially limited to one schema, which is a huge limitation. Like we had hundreds of different schemas. We did look into Firehose initially because that would be very easy and nice. But because I think you could use many different Firehose streams and then kind of get around the schema issue. But we went the route of having one single Kinesis stream and then a Kinesis solution. I will yeah, exactly. You'd need Lambda or something for Firehose to do a final, like another transformation. It certainly could work. We did explore it as well. There is something I'd like to mention, I guess, like Kinesis Analytics is also, you might know it as something you can run SQL queries with, but you can also run Flink on it now. We intend to move to that as a fully managed solution of Flink. Right now it's running on EMR. So then it would actually kind of be very automatic for us, but they just haven't upgraded to the version we need yet. So, yeah.
Very quickly, how's your experience with Flink as a solution for like stateful processing and what?
Overall, pretty good. It's been solid. Like this is all kind of new stuff. Like we've been using it for maybe 4 or 5 months now. Haven't had really any issues other than with EMR itself, like maybe the master node falling over and then we have to restart the cluster. But Flink itself has been very stable. We expected it to run out of memory, for example, if we had a big backlog of messages. But it didn't. Like it was able to actually like write files to disk and then flush when appropriate and so on. So yeah, our experience was pretty good. I'd like to talk more about that if you want to come to office hours.